Hello, everyone. Anyone have any questions before we get started?
Nope. Feeling good.
Good deal. I think I heard you right. I think you said you're feeling good. So we have a test. I will be opening up. If it don't open up today, it'll be opened up this evening or tomorrow at the latest. And you'll have at least until Wednesday to get that done. So make sure you get that done. I would suggest you try to take one of the tests really soon, like, as soon as it opens up. So start taking your practice tests already for test 2, but take at least one so that way you don't forget, and you'll have some grade other than 0 in there in case you forget by Wednesday. So make sure you take that. Remember, you get 3 attempts. It's on chapters 3 and 4, but all my tests are comprehensive, so there's some possibility you're going to do something from chapter 1 or 2 as well. So anyone have any questions on that? All right, well, I guess we'll go ahead and get cracking on the actual material.
Oh wait, I have one question real quick. When is the test going to be due?
Wednesday.
Wednesday, okay.
It'll be Wednesday at midnight. Or 11:59 p.m., let me put it that way.
All right, thank you.
No problem. All right, so what I wanted to do is, last time we talked a little bit about Newton's first law. I gave you the history, some of the history or biographical information about Newton and some of his cohorts, friends and whatnot. So this time I've got to actually apply Newton's laws, and I'm going to do it in some ways that are instructive, because I need to teach you that certain things exist. I need to teach you what weight is so we can make use of that, all sorts of good stuff. I need to learn about a normal force, all sorts of cool stuff like that. So let's go ahead and get started. I'll turn on my document cam. And the first thing I want you to imagine is an object in free fall. So an object in free fall. We've already learned about free fall. What we learned was that when an object's in free fall, the only force acting on it really is gravity. So we're ignoring air resistance and stuff like that. So you can imagine a little ball falling. And of course, you know how it's going to fall. We learned that, right? And we know the only force acting on it is the force of gravity, which is a W word, a word that starts with W. Can anybody give me the name of that force of gravity that starts with a W?
Weight.
Weight. Very good. So that's the force acting on it. Now, when we use Newton's second law, in reality, it's this fancy vector equation. The summation of forces is equal to mass times acceleration, and that's vectors. But really, normally to implement it, you have to actually break it down into components. And if you use the XYZ coordinate system, then you get one equation that says the summation of forces in the X direction is equal to mass times acceleration in the X direction. And now you're dealing with actual components of forces as opposed to magnitudes of forces. So these quantities can't actually be negative. Okay, that's important to understand, because I'm going to repeatedly write, something minus something plus something minus something. And I don't want you to think that all of a sudden we're doing subtraction. No, this sigma is a summation. It's just that they're components. And when you got them all in one dimension, which is what components are, then positive and negative just indicate direction. So you also have the summation forces in the y direction equals mass times acceleration in the y direction. Summation forces in the z direction is equal to mass times acceleration in the z direction. And you don't have to use those coordinate systems, but we often do. And in fact, you've got a lot of different ways you can write things. There's things called quaternions, where you could write, Maxwell's equations a little simpler than you do right now, which is 4 equations. Or you can use tensors, which is a generalization of vectors, and that could allow you to write Maxwell's equations in 1 equation. All sorts of neat stuff like that. What I'm going to do is I'm going to assume downward is the positive direction, and I'm going to use this one for the falling ball. So one of the things you can do to indicate direction is, and this is what they'll teach you in a statics class often, You could do something like that. And if you don't specify that this is X, this is Y, then anything vertical, we're going to assume is Y, and anything horizontal we're going to assume is X. And then you put this on here and you put a plus symbol on it. Now, if you want to be, extra certain that everybody knows what you're talking about, you can put the X and Y on it. But unless you did something weird, like you drew it at an angle or upside down, or maybe this was X and that was Y, then you don't need to label them. We're always going to assume that the right is the positive X, up is the positive Y, and a counterclockwise rotation, as we see it here, is a positive rotation, which oddly enough also gives us the fact that the Z-axis is automatically pointing out of the page. Okay, so this actually gives you 4 pieces of information. That would be normally how you do it. In this case, I'm actually going to say, okay, let's draw a point object. And that's how we start with Newton's second law. We use a free body diagram, which I'll abbreviate FBD, free body diagram. And then I draw a force pointing in the positive direction. So that's my force W. And I'm calling the positive Y direction that direction. Okay. Now that I have that, I can write out Newton's second law. The summation of forces in the Y direction equals mass times acceleration in the Y direction. Now I know, since it's free fall, the only force acting on it is this W, which I assume to be positive. So this side just becomes W. Now, do we know the acceleration of an object in free fall?
It's equal to gravity.
Right. So it's m times g on this side, and boom, we now have a new equation that we can use. That's how you calculate weight. Later on, we work on gravity, we'll find out where this g comes from. But basically, if you take an object's mass in kilograms and multiply it by 9.80 meters per second, assuming the person's at sea level, then you'll get their weight in newtons. Okay, and a newton is not very big, as I mentioned before. 1 pound is 4.48, actually 4.448 newtons. So you can see a newton's a little under a quarter pound. All right, so we now have a new expression that helps us. Now what I'm going to do is I'm going to consider a box. So this was example 1. And that was just to teach us what weight was and how we can calculate weight. Weight, remember, is a force, and it is, as a force, it has units that are equivalent to newtons. So when we talk about pounds in the British system, we're actually talking about our weight. So if someone asks you your weight here in America, we're giving them the correct answer when we say pounds. When someone asks you how much you weigh in Great Britain, they will often give you kilograms, in which case they're actually answering it incorrectly. They're giving us their mass, but they're actually answering a better question because the mass doesn't change from place to place, whereas your weight does. If I carry my fat little butt up the top of Mount Everest, then 9.8 is going to be a little bit smaller than 9.8. It might be 9.78, or excuse me, yeah, 9.78 or 9.79, something like that, in which case my weight would be smaller, but my mass would still be, a good chunk over 100 kilograms. If I go to the bottom of the Marianas Trench, I'm closer to the center of the Earth. Gravity is pulling on me more strongly. Maybe gravity there is 9.81 or 9.82, something like that, in which case my my weight is heavier. So weight is something that changes from place to place, and it has units of pounds and newtons. Question? Go ahead.
In one of the master engineering, we assume we were in an elevator, and the acceleration caused the mass to change for some reason.
Right. And in fact, that's one of the problems we're going to solve today. Is there's an apparent weight that's different than your weight, and it's again, it moves and then will change back to your actual weight, and then it'll change again. So yeah, we're going to deal with that in an elevator today.
I got the weight changes, of course, because the acceleration is different. But my question is, it also had us calculate a different mass. What would our mass change to?
Yeah, your mass would not change. That's the key rule, is your mass doesn't change. I mean, barring diets and stuff like that, your mass doesn't change from one location to another or due to one motion versus the other.
That's what I thought.
Yeah, the one instance where people might argue that it does is some people try to understand special relativity having a different momentum formula by saying that it's the actual mass that changes. So sometimes people can say as you go faster and faster, your mass increases. And there's some validity to that, at least in terms of the mathematics, but really from a physical standpoint, most people argue that no, your mass isn't changing. That's just a different formula that you have to use for momentum. So, but that's the only time it really changes, or people can talk about it, educatedly and actually have your mass changed, is either by diet, removal of a limb, cutting your hair, stuff like that. Okay. All right. Now, the next example is going to be something where I want to introduce you to a kind of weird concept that stumps a lot of people. But the concept is that inanimate objects supply forces. Okay. So let's look at example 2. So example 2, I'm going to say, let's imagine we have let's see this real quick. Let's say we have a 5.102 kilogram mass. Okay, I'm carrying a lot of extra digits there. And it's a crate and it's sitting on a tabletop. Okay. Okay. Now, I would like to draw a free body diagram for this, and then use my knowledge of Newton's laws to make some sense of it. So first off, I'm going to draw my free body diagram. And in a free body diagram, at least till we start talking about torques, we're going to pretend like all objects are point particles. So the free body diagram here, and I'm going to use the convention I normally do, which is that one I showed you earlier in red. X, Y. We're not using that rotation one yet, but I still include it. So I'm going to say my object is this little black dot, and it has a mass of M equals 5.102 kilograms. And so far, the only force I know of that's acting on it is a negative force. It's acting in the negative Y direction. And that force would be the weight, which equals 5.102 kilograms times 9.80 meters per second every second, which gives me 50.00 newtons. Okay. Now, according to Newton's first law, an object in motion tends to stay in that state of motion unless acted upon by a net external force, or more succinctly, an object will maintain a constant velocity unless acted upon by a net external force. I said this box is sitting on the table. That implies the velocity is not changing, right? So since the velocity is not changing, the net force must be 0. There's no way you can have one force acting on something and have it have a net force of 0, is there? So what we have to hypothesize is that the table, this inanimate object, is actually applying a force to the mass, and that's actually correct. And we call that force the normal force. I usually write it F with a subscript N, but some authors and sometimes me will just write it as an N vector, but that's a normal force. And if it makes you feel bad about, inanimate objects applying forces, just remember an animate object created a table and they designed it such that it would stand of its own free will, if you will, meaning you build it so it stands up and doesn't fall over. And by doing so, there's automatically some amount of force you can put on it and it's going to remain standing up. And that force is really how much normal force it can supply. If you, if you don't see it that way, then maybe you need to think about what if something like an elephant sat on it, then it would clearly give way, showing you that it did have a force acting before, it just, that force was exceeded when the elephant sat on it. So does that make sense? And in this case, it looks like the force, if you take Newton's second law, the summation forces in the y direction equals mass times acceleration in the y direction. Since the velocity is 0, and you wait a couple seconds, the velocity is still 0, and you wait a couple of seconds, the velocity is still 0, that means the acceleration is 0. Remember, velocity being 0 is not sufficient to say the acceleration is 0. You have to have the velocity being 0 and staying 0. So with that in mind, I end up getting basically the normal force, which points upward. So I'm taking that component as positive, plus the component of weight in the negative direction. So that's going to be minus 50.0 newtons. Actually, it's 0.00 newtons is equal to 0. So I find that F normal is actually equal to 50.00 newtons. So it turns out in this case, the normal force happens to be equal to your weight. But I need to show you that that's not really a general statement. We're going to find a lot of instances where the normal force is not equal to your weight. So that's another example I'm getting ready to work for you. Any questions on that? Okay, well, go ahead.
Can I have you read out the summation for the normal force?
Yes, the summation of the forces in the y direction equals mass times acceleration. That's the F normal minus 50 newtons. It's actually plus a negative 50 newtons, but not too many people take the time to write plus a negative. So really, it is still a summation. It's just the component of the force weight is actually in the negative direction, so it's F minus. That's all equal to 0.
Thank you. I just couldn't read it. I appreciate it.
No problem. These are being recorded now straight to my computer, and then I'll upload them to YouTube. I think by doing that, that bandwidth problem is going to be taken care of, and you'll be able to see them better in the videos. So the photograph of the docs are usually up within 10 minutes of the class to an hour, depending on if I got another class right after. But the videos will usually be up within a couple hours because it takes well over an hour to download it and re-upload it and all that. All right, so let's look at,
thank you.
No problem. Let's look at another example. Let's look at example 3. This time I'm going to take a 5.102 crate, kilogram crate, and I'm going to lay it on the floor. And I'm going to assume it's frictionless, mainly because we haven't studied friction yet. And that's partly why we're studying the normal force, is because friction is going to come into play. Oh, actually, no, I will include friction, but I won't tell you how to calculate it. So what I'm going to do is I'm going to say there's a force acting on it, and that's a friction force of, let's say, 10.00 newtons. And I'm going to say that's the magnitude of the friction force. Notice that fancy looking curly F. That's what I use for my symbol for friction. So if you see that, you should know that's what's happening. What I'm also going to do, though, is I'm going to say there's a force acting on it this way. And this force is going to be 200.0 newtons. And it's going to be at 30 degrees above horizontal. Okay, so in other words, this is like me in a Home Depot pushing a box I don't want to carry, right? So I'm walking and the box isn't that tall, so I lean forward a little bit and my arms are at a 30-degree angle with the horizontal, and I'm pushing it along. And evidently there's some friction involved, and that friction is the 10 Newton force pushing backwards. I'm not showing you yet how to calculate such a thing, but we will next chapter. What I want to do is calculate the acceleration, the normal force. So A is equal to question mark, and F normal is equal to question mark. So again, I'm going to use my convention. All that's plus, and I'm going to draw a free body diagram. So I'm going to say this is 5.102 kilogram mass. Now I have acting on it a force in the negative y direction of 10.00 newtons, and that's actually equal to F. I also have, excuse me, I said negative y, I meant negative x. I also have a force acting on it in the negative y direction, and that's the weight, which we've already worked out as W is equal to 50.00 newtons. We have a force in the y direction that's positive, and that's going to be the normal force, F sub n. And then we have this force that's not aligned along an axis yet, so I had to draw it black. Okay, and that's 200.0 newtons, and that's just F. Okay, so I need to break that down into components as well. You can see it has a x component in the, or excuse me, a y component in the negative direction. So I'll put right here and call this F sub y. This is 30.0 degrees again. And then it actually has a x component that points in the positive direction. So I'm going to use purple for that. So I see that this is F sub x. You can probably see, hopefully you know this, that Fy will be equal to 200.0 newtons times the sine of 30 degrees. And of course, you know your special triangle. Your special triangle is 60, 30, root 3, 1, 2. So when I take the cos or the sine of 30 degrees, that is opposite over hypotenuse. That's 1/2. So that one's going to be 100.0 newtons. And that's just the magnitude of it. I haven't decided on the sign yet, but as you can tell, the sign should be positive. Hence, I wrote it in purple. And then F sub x. Ooh, I actually wrote it in purple, even though it was y. So let me keep writing it in purple so it won't be throwing anybody off. So F sub x is going to be 200.0 newtons times the cosine of 30 degrees. And this time it's root 3 over 2. So if I take the 2 in the bottom, that'll cancel out with the 2 and the 200. That'll give me 100. So I'm just doing 100 times the square root of 3. So that's 173.2 newtons. Okay. Now I've got all of these magnitudes computed, and I can use Newton's second law. So Newton's second law in the x direction and Newton's second law in the y direction. Let's do the y direction first. The summation of the forces in the y direction is equal to mass times acceleration in the y direction. Now, I'm sliding this box along the floor in Home Depot. I do not see any reason for the box to be going bouncing up and down, right? And in fact, its vertical velocity is always going to be 0. So because its vertical velocity is always 0, that means the acceleration in the vertical direction should be 0. That also means the acceleration in the in the x direction is the only acceleration it's going to have. So I'll just call that one A instead of A sub x. But now, because of this, I can write all the forces in the y direction add up to give me 0. So in the y direction, I have F normal pointing up. So I'll say F normal. I have Fy pointing down. So I'm going to say, well, that's negative 100. And then I have W pointing down. So I'm going to say that's minus 50.0 newtons. And that seems to be all of them. That's 1, that's 2, that's 3. Yeah, that's all of them. And that's equal to 0. So I can immediately find that the normal force, if I pull the 50 and the 100 over here, it's going to become positive. So it's 150.0 newtons. And now I have the normal force. So this is an instance where I'm showing you again an example to make sure you don't make the mistake that the normal force is always the weight. Clearly, if I'm pushing downward on it as I am here, I'm actually increasing the normal force. And in fact, when you were smaller and you used to cut the grass, say with a push mower, assuming you did, your body sort of understood physics enough that you would start off pushing the lawnmower like this. Maybe you're tall enough where you can just push down on the handles a little bit. But after a while, you got so tired, you ended up making your arms go horizontal. The actual handles for the lawnmower, which would normally be like this when you're pushing like you were. Now the handles are going to go more angle and you're going to push perfectly horizontal. And what it is your body realized it's a lot easier to do that because now I'm pushing horizontal. All my force is going into moving the lawnmower and none of my force is going into making it harder. And in fact, if I push up a little bit, it's actually going to make it a little easier because the lawnmower won't sink into the ground quite as badly. So your body sort of knows a little bit of physics just from years of experience. So now let's do the summation of forces in the x direction. So the summation of forces in the x direction equals mass times acceleration in the x direction. Remember, that's the only acceleration now. So I'm just going to call it A when I write it on the other side, and we're going to solve for that. Now I just got to take all the x component of forces. I see that I have one positive, F sub x, and I have one negative, and that's the friction. So I'm going to say F sub x, which is 173.2, minus 10.00 newtons is equal to the mass, which is 5.102 kilograms, times the acceleration. Notice I just called it A that time. And you can see that A is going to be equal to 163.2 divided by 5.102. So 163.2 divided by 5.102 gives me 31.99. That 5.102 is 4 sig figs. This is 4 sig figs, so that works out fine. In fact, I could call it 987. I'll do that to carry an extra digit. Meters per second every second. Now I have the acceleration of the block. So these are sort of kindergartner level Newton's second law and third law and first law equations, okay, are problems. I didn't even have to employ the second or the first, I mean the third or the first law on this one, but that's what it is, 31.987. And again, these were mostly instructed to show you how it's going to work out. You're going to have to break vectors up into components parallel to the certain axes. You're going to have to give them the proper signs so that they can be added or subtracted, even though you're always adding them. And then ultimately you're going to have to solve for the acceleration. So any questions on that?
Nope.
All right, well, let's attack that elevator problem now. So this is going to be example 4. And I like this because this is one of the things I used to do with my little girls. I'd take them to my campus when it was closed on weekends. And we'd ride the elevator inevitably because it was kind of fun for the fear of getting stuck in an elevator on a weekend. But basically, we're going to imagine a person riding an elevator with a scale on it. So we got a scale in here, and we got a person in here of mass M. Okay, that scale is going to weigh your apparent weight. Okay, it's going to read the force required to hold you up. And that is exactly what your apparent weight is. But we're going to examine it in a case where, let's say the mass is actually going to be a 50 kilogram kid. Okay. And we're going to examine it in a case where the acceleration is going down at 2.00 meters per second every second. So what I've noticed, and probably you all noticed, and I, of course, have completely taken advantage of it and continue to do so because I'm still really just in 3rd grade. And that is that when you first take off upward in an elevator, you feel heavy. So I always, let my legs bend, my knees bend really good and squish down. And then, of course, as you're going up, and you come to, say, the 5th floor, which is where you're going to get off, the elevator will start to slow down. That's acceleration in the downward direction like we're seeing here. And you'll feel light. And in fact, I always take that opportunity to jump, which really embarrasses the crap out of my daughters because I do it whether people are in the elevator or not. Well, unless I'm sick or something where I don't feel good. And in fact, I've done it so well that I've actually hit my head on the ceiling of the elevator before. So that's kind of fun. And I've done it so rapidly that I once got our elevator sort of cattywampus inside of our elevator shaft and got locked in there. That was exciting because it was a weekend. Nobody was around.
No
and those
way.
games don't always work. Yeah. So that's why my daughters get scared. But anyways, it's all for the matter of science, right? All right, so what I'm going to do now is imagine the scenario where the acceleration is downward. So this could be them letting you free fall for the first couple seconds, getting on the elevator going down, or it could be them slowing you down on the last couple seconds of the elevator on their way to go up, both of which you recognize as things that make you feel lighter. And I'm going to show you why. And then all we have to do to address the other way is change this acceleration from pointing down to pointing up. And you'll see exactly why we experience what we do. So let's draw a free body diagram again. I'm going to use my same sign notation. And it's getting rough, clearly. It became a triangle. I don't know what that means, but anyways. So here's my object. It's a 50 kilogram child of mass M equals 5.00 kilograms. The child has a force acting up on it in the upward direction. That is the weight, the force of the scale, which is really your apparent weight. So I'm just going to call that F scale or F sub S, right? Now you're going to have a force acting down, which is actually your weight, mg, which is basically 490 or 49, excuse me. Lest I be a goober. Yeah, 490 newtons. Okay. I was gonna say it was 49 instead of 490, and I was like, wait a second, let me double check that, make sure I'm not an idiot. Okay, so these are the forces acting on it. Now in your dynamics class, they'll teach you to draw free body diagrams and acceleration diagrams often. So we don't do that in physics, but what I will do is I say the acceleration is going downward. So A is equal to negative 2.00 meters per second every second. And I'll just put that off to the side to remind us of that. So now I've got to take Newton's second law, the summation of the forces. Notice I'm only dealing with the y direction, so I only got to do one of them. The summation of forces in the y direction is equal to mass times acceleration in the y direction. So this is going to give me the two forces, the F scale, which is positive, minus the 490, which is really just mg, by the way. And that's going to be equal to the 50.0 kilograms times the only A we know. Okay. And that A, of course, is the negative 2.0 meters per second. I'm saying it's the only A we know, so I don't have to subscript it. Okay. So I can get that the force on the scale is going to be actually equal to 490 newtons plus 50.0 kilograms times negative 2.00 meters per second, which is your MA term. So notice it's the weight plus MA that your force of the scale is. In this case, the MA is negative. So I get 490 minus 50 times times 2. And in this case, I get 390 newtons. So you see, you normally weigh 490 when the object is accelerating downward, either by slowing down on the way up or by speeding up on the way down, you feel lighter. Okay. And you can also tell that if I had chosen if we chose this, then this sign would be positive. And it would give you, in fact, instead of 390, it would give you 590. So you can see why both things occur. On the way up, if you're accelerating upward, then this is going to be a positive and you're going to feel heavier. You're going to feel like you're 590 newtons instead of 490. But if you're on the way up slowing down, you're going to feel 390, which is lighter. Or if you're on the way down speeding up, you're going to feel lighter at 390. Or if you're on going down and slowing down, then that's an acceleration upward, so you're going to feel heavy again. So this actually covers all 4 instances. Isn't that kind of neat? Now, again, as I told you, your weight doesn't change. Your weight changes in that to your apparent weight. In some sense, it's almost like your weight didn't change. You just had an apparent weight, but your mass doesn't change at all. So that's something to keep in mind. Your mass will not be changing as a result of this motion. Any questions on that?
One comment is when someone else talks, and the Zoom goes to theirs and it comes back, the screen's really clear after that. So,
Oh, really?
Yeah.
The screen gets clear as a function of audio, huh? That's crazy. Well, it makes sense. It's the good news is all of that should be remedied on the video when I post it, because that's a bandwidth that I suspect is between my Wi-Fi and my internet to wherever, and your Wi-Fi and your internet to wherever. So hopefully we're cutting all that out now. Any other questions or any questions?
Yeah, this is regarding like how the notes are posted in the drive. I think you went over it before, but what's the naming scheme again?
I always start it with like today's will be PHY _ 241 _ D01C. And then I'll do something like Ch4Fin, where because I'm finishing chapter 4. But the most important part, and this is probably the only part you'll never need to search for, is the 091621, because today's September 16th, 21.
Okay, I see. Thank you.
So yeah, when you do that search, the only reason why I reminded you where all the other stuff is from, so you don't accidentally grab one from another class. You might prefer your own. Okay. All right, so there's 4 big examples, but that's not all of them. In fact, there's 2 more big examples I'd really like you guys to understand. We've now seen something about apparent weight. We've seen how the normal force can actually change. It's not necessarily going to be your weight. Now I'm going to do something that is an equilibrium problem. It's also called a statics problem. So it should be, if you've had statics already, it should be pretty straightforward or simple. What I'm going to do is this is going to be example 5. And I'm going to imagine a long rope, like a clothesline. And in fact, this angle right here is going to be 60 degrees. And this angle right here is going to be 36.9 degrees. And what we have is a child playing on the clothesline by hanging from it. Okay. The child has a mass equal to 50.0 kilograms. And this could be written as 60.0 degrees as well. What you can see is what's holding this up is really a tension that I am going to draw as just blue until I compute the units. So that's going to be what I call the tension on the right. And this will be what I call the tension on the left. Okay. So I know that's not that easy to see. That's why I'm drawing it extra dark as well as I can anyways, but I just don't want to use red or purple. And also black wouldn't show up very well in that rope. Okay. So what we have is a situation where a girl is hanging from this of her own volition. Okay. Or a boy or whatever, a small child. And it's by hanging there, they're not accelerating. Their velocity 0 and then 0 and then 0. So again, it's not no velocity. So, and it's never any velocity. So the acceleration is 0. We can use Newton's second law to actually solve for TR and TL. But you see, of course, there's some reason to believe that the tension in the left side of the rope is different from the tension in the right side of the rope. And in fact, if you were doing this in a conceptual physics class, I would remind them that these two vectors have to add to give you the equilibrium of this vector. And the equilibrium of this vector is just the opposite. In other words, the same length vector, but negative. So when you go to do that, you can actually figure out which one's going to be larger. So let me show you what I mean by that. Let's say the weight is this vector. Okay. Let's say, obviously, one vector is going to be along this line. The other vector is going to be along this line. Well, actually, I should make it even more severe. So the other vector is going to be along that line. What you have to have is that the sum of those two vectors has to be exactly the same as this. So I'm going to go up the same distance, which is right about there, and I'm going to go straight up. So these two vectors here and here have to add up to give you this vector, because this is the same length as that, supposedly. This,
Professor, what is that? What is that second angle? Not the 60, the other one.
36.9
36.9.
degrees. Yeah.
Okay.
I'm trying to stick to those special angles so I don't have to pull out my calculator every second. So what we know is this vector, this component, this way has to be parallel to this one. So I'm going to do like this, and this component has to be parallel to this one. So I'm going to do like this. And you can see from that, that this vector is short and that one's long. That's TR and that's TL. Okay, so I'm a conceptual class. That's the way I work it, because they don't do trigonometry in a conceptual physics class, right? But you can see by the way vectors add is it has to be this, and because this angle is so big, this vector is going to be quite small and this vector is going to be quite large. So we expect TR to be bigger than TL. Does that make sense? So that's our predicting the answer before we actually do the answer. And I'm going to put this blue pen away because I hate it. Now, that being said, let's do the summation of forces in the x direction equals mass times acceleration in the x direction. But as I told you, the child is not moving nor ever. So it's going to be acceleration equal to 0. And I got to draw a free body diagram. And I'm also going to do the summation of forces in the y direction equals mass times acceleration in the y direction. But again, it's not moving, so the acceleration is going to be 0. That's a key point. Remember, like when you're swinging on a swing, you go like this and back up to like that. That point right there, your velocity is actually equal to 0, but your acceleration is a maximum. Similarly, when you get right here, your velocity is a maximum, but your acceleration is equal to 0. So don't confuse velocity and acceleration for each other. That's why I'm stressing that it's not just that the velocity is 0, it's that the velocity is 0 and still 0 and still 0. So let's draw our free body diagram so I can fill out these. My free body diagram is going to be a mass of 50.0 kilograms. I'm going to have acting on it a force which is not along an axis. So I'm going to draw it black, and that's TR. And it's going to be a force that's not along an axis. So I'm going to draw it black, and that's TL. And then I have a force pointing in a downward Y direction. So my directions rule for this one is going to be that. So this is going to be 490.0 newtons. Actually, I'm carrying an extra digit there, so I'll put that underlined. So now my axes go like this. And that's my x-axis. And that's my y-axis. This is the 36.9. And this is the 60. Okay. So you can see that the right tension is going to have a positive x component and a positive y component. The T sub L is going to have a positive Y component, but it's going to have a negative X component. So this is TLX. This is TRY, TRX. Like I just changed that all of a sudden. And this little guy in here is TRY. Now from that, I can see that TRX, notice that is opposite the 36.9 degrees. So that's going to be just TR times the sine of 36.9, which if you remember correctly, the 3, 4, 5 triangle, there's the 4, there's the 3, there's the 5. This is the 53.1. This one's the 36.9. So if I take the sine of 36.9, I'm getting 4/5. So this is 4/5 TR. The TRY is positive as well, so I'll write that in purple. And that's just TR times the cosine of 36.9. And is 4/5 really right? 36. Oh, look, everybody, I drew this backwards. This was bothering me. I didn't think that was supposed to be 4/5. Notice the big angle, the big side's supposed to be opposite the big angle, and I wrote it exactly the opposite of that.
Yeah.
So this one's supposed to be 53.1, and this one's supposed to be 36.9. That makes it much better. So now you can see the sine of 36.9 is 3/5. Glad I was paying attention to that. I hate it when that comes up bad. So this one's going to be, of course, the 4/5 part. So that's going to be 4/5 TR. So we've got the X and Y components of TR. I need the X and Y components of TL now. So TL is the X component is going to be negative. So I'll write TL sub X is equal to negative TL. The X one's going to be the sine of 60, given by the sine of 60, I should say. Of course, our sine of 60, if we remember our previous triangle, the sine of 60 is √3/2. So I'm going to use that negative square root of 3/2 times TL. And then the TL sub Y is a positive one as well. So that one's going to be positive TL times the cosine of 60. And of course, the cosine of 60 is 1/2, which you can see here, 1/2. So this was just going to be 1/2 TL. Okay, so now I've got all those components worked out. I can actually fill out my Newton's second law. So the summation of forces in the X direction is just this guy and this guy. So it'll be 3/5 minus √3/2 times TL. Oh, excuse me. No, it can't be that. I was thinking they were both the same tension. 3/5 TR minus √3/2 TL is equal to 0. So I don't need this parenthesis here either. Everybody agree with that equation? We'll call that equation 1.
Yep.
Okay. Now we're going to do the Y. And in the Y case, we basically have the weight, which is negative, but we have these two guys, which are positive. So I got a 4/5 TR. And I got a 1/2 TL. And I got a minus 490. equals 0. I'll call that equation 2. Okay. So if I do something smart, I can actually solve the system of equations an easy way. I'm going to rewrite equation 1. That's 3/5 TR minus root 3 over 2 TL is equal to 0. And then I'm going to write this other equation as 4/5 TR minus 1/2 T, dang, I did it again, TL is equal to 490 newtons, like that. Okay. Now I'm going to multiply both sides by -3/4.
Why is tension 2 negative in the second equation?
Let's see. Oh, it wasn't supposed to be. Good catch. Thank you. I did it correctly there, but I didn't do it right here. Thanks. Nice catch.
Thank you.
That's the kind of crap that'll screw me up if I don't. So notice I'm multiplying it by 3/4 and by a negative. And the reason being is this 4 is going to cancel out with that and give me a -3/5 TR and a +3/5 TR. So I can add those equations and get no TRs. So that's a way I can actually eliminate the TR. So in this case, I get 0 TR after adding the equations. So that one's gone. But in this case, I get what? 3/8 minus root 3 over 2. So I'm going to say 3/8 minus square root 3 over 2 times TL, which I can actually fix that. I mean, I can get a common denominator and make that look like a not quite so horrible number. And now I'm going to take 490 and multiply it by -3/4. Oh, and this should become, because that's a negative, that should become a plus here. It was already a plus, no, so it should become a negative. So yeah, I got it right now. So now I'm going to do 490 times -0.75. And I get -367.5. Okay. So getting a common denominator, I can just multiply this by 4 and that by 4. So this would be 3 minus 4 root 3 over 8 TL is equal to, I did say negative. That's going to make that negative. That's going to make that negative. Oh, both of these are supposed to be negative. Okay, that's cool. Don't forget that guy up there was supposed to be, no, that one was positive. Oh, I was doing the wrong one. So that one's negative. That one's negative. So yeah, they're both negative. Sorry about that. So that's 3/8 and that's negative. Okay, yeah, good. Whew. Scared me because I was getting a negative on this side, 367.5 newtons. So now all I got to do is take that crappy number, which is admittedly a horrible number, right? And that'll give me TL. So I can say TL is going to be equal to, obviously I'm going to get rid of the negative, but I'm going to take that 367.5 and divide it by that nasty number, which is 3 plus the 4 times the root 3. 3 plus 4 times square root 3. Enter, and now I'm going to divide that by 8. Okay, so that's 1.24. So that's going to be 367.5 newtons, which is an extra sig vig, divided by 1.241. That's a pure dimensionless quantity. So I get 296.1 newtons, and I'm probably carrying an extra digit there. I've stopped paying attention to digits here when I started doing fractions, so take these underlines with a grain of salt. Now that I have that, I can plug that back into any one of the expressions and get what TR is. So for instance, I would like to do that one. So now I'm going to say 3/5 TR minus square root of 3 over 2 times 296.1 newtons is equal to 0. So that's going to give me TR is equal to basically this times 5/3. So let's say 296.1. I'm going to take that and multiply it by square root of 3. And I'm going to take that and divide it by 2. And now I'm going to multiply by 5/3. And I get 427, which was consistent with our prediction, which was the right hand would be bigger. So at least our result is consistent with what we expected based on the way I teach it in my conceptual physics class. Any questions on that? All right. We've got about 15 more minutes. I'm going to show you another example if no one has any questions.
Cool.
This one's a fuzzy dice problem. So imagine a car mirror, which looks like this. Okay. And you normally have fuzzy dice, which has a center of mass, but I'm just going to treat it like a ball, basically. Okay. Because that way, the problem is when you deal with a fuzzy dice, it's not necessarily centered on directly under it. So it'll be all cattywampus. So I'm just thinking about that right now. But what we're going to be doing is we're going to be driving in a car that's accelerating this way with an acceleration A. Okay. Due to that, the fuzzy dice is going to swing back to some angle like this at some angle theta. And the ball is going to be there. Okay. So I'm going to use Newton's second law to find out what angle that is for a given acceleration. So theta equals question mark if we assume we know A. So we're pretending like we know A, and we're going to solve for theta and hope we don't need anything else. I'm going to make some assumptions. I'm going to pretend like the ball has a mass M and stuff like that, but I'm not really going to specify it. And I'm going to hope that it all cancels out. Otherwise, it's going to be different for different mass fuzzy die. So here's my free body diagram. My free body diagram, again, using my normal sign convention, is going to be a tension up. Actually, I should draw that black since I haven't put it in a axis direction yet. That's my tension. Okay. This angle here is theta, which means this angle right here is also theta. Okay. So this is my y-axis pointing up, and this is my x-axis pointing to the right. Now, the other force acting on it, does anybody know what other force might be acting on it?
Gravity.
Gravity. So that's right here, and that's weight equals m times g. Okay. So we can see that we have a vertical negative component of force, namely weight, but then the tension is going to have a positive x component, T sub x, and it's going to have a positive y component, T sub y. In fact, the y component is going to have to completely be equal to the weight, or it's not going to work. And the x component is going to have to equal to the force required to accelerate this thing at an acceleration A, or it's not going to work. So that's sort of the physics of this. Now let's work it out mathematically. So I can see Ty, of course, using this as theta, is equal to T times the cosine theta. And Tx is, again, using this as theta, Tx is equal to T sine theta. So the summation of the forces in the y direction equals mass times acceleration in the y direction. There's no acceleration there. We're basically saying it's going to reach equilibrium as long as he's accelerating at a rate A. Then my acceleration in the y direction, or my Newton's second law in the y direction equation, becomes T cosine theta minus mg is equal to 0. But I'm going to write that a little smarter because I know what's going to happen. So I'm going to write that as T cosine theta is equal to mg. And that's going to be equation 1. Now the summation of forces in the x direction equals mass times acceleration. Since it's the only acceleration, I'm not even going to subscript it x. I'm just going to leave it a. So now I see that the only force is T sine theta. That's literally the only force in the x direction. So the right-hand side is just m times a. And that's going to be equation 2. Now, the reason I show you this problem is 1, because it's cool, but 2, because this is a way you can solve a system of 2 equations, 2 unknowns that you usually don't learn in your math class. And there's reasons for it. I mean, and I'll tell you that as I go. But what I'm going to do is take 2 and divide it by 1. That's a way they don't teach you in math usually. The reason why is when you divide by something, if either side is 0, you could get a nonsensical answer. So that's the danger of it. But when I divide them by each other, I get T sine theta over T cosine theta is equal to MA over MG. You can see the T's cancel out, and you ultimately just get tangent theta equals A over G, or theta equals the tangent inverse of A over G. Okay. Now, if you wanted to go back and see what the tension is, you can do that as well, but it helps you to have a little trick. If you use this trick, tangent theta equals A over G, then you can make a right triangle, and you can say this is A and this is G, and this is theta. And since that's a right triangle, you know this is A squared plus G squared. So now I can actually evaluate what theta is, and I can take, for instance, the equation, let's say 1, which is T cosine theta equals mg. Well, that's going to become T. Now the cosine of theta would be adjacent over hypotenuse, so that's G over the square root of A squared plus G squared. And that's all going to equal mg. So you can see what happens is that T, I'm going to have to divide by this, that G is going to cancel out. Is that G going to cancel? Yeah, that G is going to cancel out because I'll have a G on the right under this, and then I'll have the square root on top of this. So it's going to be T is equal to the M times the square root of A squared plus G squared. And notice that does have the right units because A and G both have units of acceleration. They're both squared and under a square root, so it should be M times acceleration. So that's a neat little problem. And that leaves me with exactly 1 more left. Okay, anybody have any questions on that?
I saw the same video on your YouTube.
Yeah, we did the same. Yeah, I did the exact same problems yesterday. And I thought I did pretty good. This one actually video seems to be going a little better, except I seem to have made a few more mistakes. But it'll be up there anyways. All right, our last example. The last example we're going to do is the Atwood machine. And an Atwood machine basically is anytime you have a pulley with 2 masses hanging on it, then you try to compute the acceleration and the tension in the rope. That's an Atwood machine. We're doing the special simple case right now where the pulley has no mass and no friction. So what I'm going to do is imagine a really big mass, big M, hanging from this, and of course quite high, and then a really small mass, little m, hanging quite low. Now, if I didn't care about the tension between them, I could work my way through a Newton's second law using just one Newton's second law application. But doing so would have to treat M and M as one big mass. And things get complicated. It's really easy to make mistakes. So really, it's better to do F equals MA for both of them, for each of them. And then you also get the free information about the tension in the cord, because that's an internal force if you're just doing it as one body. So what I'm going to do now is draw a free body diagram for the left-hand side. So this is my left-hand side free body diagram. And I'm going to say up is positive. And the trick with this is once you say
Professor, you're writing outside the camera.
Oh, thank you. I said left-hand side free body diagram. The trick with the Atwood machine is when you decide one side is positive, like if this side's positive going up, everything that's consistent with that has to be positive. So this side going down is now going to be positive as well. Okay, this side up is positive, this side down is positive. So here's my free body diagram. I have a mass, big M. All I have acting on it is this mass is like, hey, I'm trying to fall at a rate of 9.8 meters per second. So I've got this force, mg, acting on me in the downward negative direction, but the stupid tension, the stupid rope behind me is slowing me down. And that's the tension. Okay. Now I have a free body diagram for the right-hand side. This time, of course, that means, and I actually wrote that exactly backwards. I used a red marker instead of a purple one. This side down is positive. Okay. So now, according to the mass little m, it wants to fall at a rate of, actually, it's trying to fall at a weight little g, but in fact, a tension T is pulling it up. And they're the same T, because if they weren't, if this T was larger, that would be a result of having to not only lift this mass over here, but also lift the string, combat the friction in this pulley, and combat the inertia in this pulley. Because it doesn't have any friction or inertia in this pulley, and the mass is, and the rope is massless, these two tensions are equal. So now I can do the free body diagram. I can use that to derive a Newton's second law, summation of forces equals mass times acceleration. Now, unless this string were to go slack or to stretch, then every time this string moves 1 inch, this string's going to move 1 inch in that same amount of time. So the accelerations are actually going to be equal as well. So for this one, I get T minus M, that's actually supposed to be a big M, T minus big M G is equal to big M A. That's going to be equation 1. And then this side, the summation forces equals mass times acceleration again. On this side, it's going to be little mg minus T is equal to little ma. And that's going to be equation 2. Now I can add them. Notice the T over here is positive and the T over here is negative. So adding them is the natural choice because it's automatically going to cancel out the T. So I'm going to say 1 plus 2, and I'm going to get T minus mg equals ma plus negative T plus mg is equal to ma. And you can see what happens. I'm going to get big M minus little m times G is equal to big M plus little m times A. So A is actually equal to M minus M over M plus M times G. And we often write equations like that in physics. We ideally would like to have some number that has no units, like M minus M over M plus M, times the number with the unit that matches what you expect it to have. That way you're really quick on doing the unit analysis. Now that I have that A, I can plug it in equation 1 and solve for T. I didn't get the time to do that on my other video, so I'll give you guys a favor. And so equation 1 and 3 is going to give me T minus mg equals big M times M minus M over M plus M times G. Now that looks horrible and it might be scary, but it's really not that bad. I'm going to pull this over to here, the mg over there, and that's going to become plus mg, but I'm going to get a common denominator. So I'm going to say m times m plus m, all of that over m plus m. Now this one already had m times m minus m times m. So this will be minus m squared minus mm. And then all that will be times g. Working this out, you can see I'm going to have m squared plus m minus m squared. Make sure my signs are all right. Make sure I got that right. So this came over here, became positive. It would be m, it would be m times m plus m. Yeah, that works. This over here would still be positive, it'd be m. This one was supposed to be positive, wasn't it? Yeah, this was supposed to be positive, only this part was supposed to be negative. So I've got that. I think that's right. Anybody see any errors in this? Seems like I got a sign error or something somewhere. This is definitely right. This is going to be equation 1, so that's m times a and that's m times g. That's right. M times m minus m over m plus m times g. That all works. So that's going to become big M squared minus m big M. This comes over here, does become a positive m. I multiply it by that, so it'll be m squared plus mm plus m squared mm. Okay. All that's going to be over m plus m times g. So when I get this, it looks to me like what's going to happen is the m's are going to cancel out, and I'm going to get 2m squared over m plus m, which is exactly the opposite of what I thought I got when I did this. But you can also write it as t is equal to 2m over m plus m times mg. Again, that way you have a unitless quantity times a unit quantity with the units that you want. I really thought this worked out to be 2 little m big M. So you might want to keep an eye out for an error when you're going over this. But I could just be misremembering it because I hadn't done it in a while. So keep an eye out. But that should do it. Okay. So I definitely recommend you guys try to work that out yourself. I think your book probably does it too. I don't know if they actually solved for the tension, but if you look in there, you should be able to find it as well. We have now finished chapter 4. And as I said, I'll open up the test and you guys will have plenty of opportunity to take the practice test plenty of times. And then you have until Wednesday to do the test. And I'm not seeing the Atwood machine like I expected to see it. I know it's in here somewhere. Oh, might be because I was looking in chapter 5. That wouldn't help. So anyways, if y'all find the error, let me know what it is. That'd be helpful if there is an error. But I'm thinking maybe all this time I've been misremembering it. So you're free to go. Time's up. And I'll wait here for the last person to leave. If anybody has any questions, I'll wait around.
Thank you.
Thank you. Thanks for coming, everybody.
Yeah.
Quick question.
Yes.
So for the homework, there's a lot of there's stuff from like chapter 6 and stuff coming up. What chapter have we covered so far?
We just finished 1, 2, 3, and 4.
Okay, so everything up until chapter 4 is like I can work on that.
Yeah, and all the dates on 5 and 6 are meaningless. Or
Okay,
anything later than 5 and 6.
But dates on up to 4 are correct?
Yes.
Okay, cool. Thank you.
No problem. Have a good one.
You too.
So, yep, I found the error. Notice I was treating up as going positive. That's actually the opposite direction everything's going to go. And you can tell that because when you ultimately did this, here's where my mistake came in. So my mistake came in there. I'm not going to tell you what it is, but I think you can find it pretty easily. And because of that, I'm going to get an acceleration that will be the negative of all this. So this becomes negative, and then ultimately all these signs will be reversed, and that'll actually make it get what I expected. So I did put a note down here. I expected it to be 2 little m times big M times G over M plus M. And then, yep, I found the error. So you guys should try to find that as well. You folks that are looking at this, I think it'll be a worthwhile exercise, and it's just a no-brainer that I did because I just by rote remembered everything, but I ended up doing these two in the wrong directions. Again, I treated the direction upward as if the big M was going up, that as positive. And ultimately, that's going to make this acceleration come out to be a negative, and that's going to make that sign different. And you can see where that negative should have came in if you look in this area, because this is where the mistake is. So have a good day.